Hello, and welcome to continuation of Module 5. We're going to be, let me share content with you. We're going to be advancing our study of irrational expressions. We're looking at a copy of our list of assignments. We're looking for today's date is the 18th of October. So what we're shooting for on our list of assignments is due date of Sunday, the 23rd. Okay. So last time we were together, we were almost done with section 6.2. I would like to conclude section 6.2 from our calendar. We're seeing, I want to work on student practice number 7. So let's shoot over there. Here's our textbook. And I've got this preloaded for us. And here's a copy of our a whiteboard for us to work on, okay? As if we're actually in the classroom, thanks to the wonders of technology, all right? All right, so let me go ahead and begin. And, all right. So here is section 6.2. Example, actually, we're not doing example. Let's do, this is actually student practice. Example number 7 didn't present the complications, that student practice 7 that we're looking at right now has. So that's why I'm choosing this example. It is a little more challenging and more typical of what your homework is going to present. Okay, level of difficulty, if you will. 4x plus 2 over x squared plus x minus 12. All of that rational expression minus 3x plus 8 over x squared plus 6x plus 8. I'm just going to make sure I copied it correctly. 4x plus 2 over x squared plus x minus 12. And all of that first rational expression minus 3x plus 8 over x squared plus 6x plus 8. And the instruction that we read is subtract. Okay, one word instruction. So let's max out the view of this window. Gives plenty of room to work. And the first thing, that we've been working on, this week is when you do add or subtract, even if it was fractions, here we're adding or subtracting rational expressions. The first thing we look for is we try to determine whether the denominators are the same. So I ask myself, hey, self, are these denominators the same? And I compare part for part. I go, all right, x squared, plus, oh, there's the first difference. This guy over here has a 1x, and this guy, the other denominator, has a 6x. As soon as I saw that, if there's one difference like that, I have to come out and say, nope, these denominators are not the same. As soon as we identify different denominators, we have to create, find, calculate, an LCD. We need an LCD to proceed. Okay, least common denominator. We have 4 steps to doing that, to finding the least common denominator. The first step is to list both denominators. We have x squared plus x minus 12 is our first denominator, and then x squared plus 6x plus 8 is our second denominator, just the denominators, the LCD, the LCD is based only on the denominators, right? So next step is to factor. We factor our denominators completely. So I'm looking at this, there's no GCF in this, we're looking at this first polynomial. I'm looking for GCF, none to be found. Then I go, is it a perfect square trinomial? I go, no. because even though the first term is a perfect square, perfect squares in the last term, perfect squares are never negative. So I abandoned the perfect square trinomial approach and realized that I have to leading coefficient of 1, factors of C whose sum is B, where B is 1. It's an invisible 1. So I'm thinking when we factor this guy, x times x is going to make the x squared term out of the f, in FOIL. And then what are going to complete the terms that are going to complete this are going to be the factors of C. C is -12. And they're going to add up to 1. What factors of C and what factors of 12 have a difference of 1 are 3 and 4. When we have to multiply them, they have to make a negative, 12, negative. So one has to be positive, the other one has to be negative. But I've got to come out, when I add them together, I have to come out having $1, which is B, the sum table of the two tables method. So I'm going to have the 4 be positive and the 3 be negative. And then I think we're good to go. When I multiply these together, we get -12. And when we add them together, we get +1. Now, in the factor step, the way we said on Tuesday's lecture, I need the exponents showing. There's only one of each of those two binomials. Okay, so I raise them. I want those showing, those exponents. Okay, let's hop over and factor the second denominator. Similar conclusions that the last term is not a perfect square, even though the first term is. I'm going to treat this like a trinomial with a leading coefficient of 1. X times x gets us the x squared. Factors of 8 whose sum is 6. So I'm thinking, 2 and 4, and everything's positive. Factors of C is 8 whose sum is 6, B. Both of these are going to be positive. Okay, so raise them to the first because they already are, because we're completely factored. Again, there was no GCF, nothing like that. We were able to go straight to factoring using the two tables method. Okay, in this step, we're ready to go to populate the LCD by including one of every different kind of factor. And so the way we shorten this down to a more helpful keyword is unique factors. The LCD contains one of everything different. So x minus 3 is the first of its kind, the first factor in all the denominator factors of its kind. Then x plus 4 is the next factor of its kind. So we have to include those. Those are all the different kinds of factors in the first denominator. And then we head over to the second set of factors from the second denominator. X plus 2 is not represented yet in the LCD, so we have to include it, something different. And then x plus 4, we look at this guy, but it's already in here, so we don't do anything. We don't include the second x plus 4. Now the last step is actually very important. The last step of creating an LCD, calculating an LCD, is we want to raise each of those factors to the greatest exponent that we find across all the factor trees on each factor. So I look at x plus 3, I find it in the factor trees. It only appears in this first denominator, whatever its exponent is, I need it all. Then we're looking at x plus 4. X plus 4 does appear in both denominators, so I compare their exponents, but they're both the same. They're both 1. Neither one is greater than the other. So I just grab a 1 from either occurrence and put it on the x plus 4 that's in the LCD calculation. Then we finally, x plus 2 only appears once in the second denominator, whatever its exponent is, which is a 1. We need all of it. Okay. Simplify this LCD, meaning, whatever the exponents, if they're all to the first, we can get rid of them. X minus 3 as a binomial to the first power is itself. X plus 4 to the first power is itself. And x plus 2 to the first power is itself. Here's our LCD. Okay, what do we do with it, the LCD? Well, here's what I would like to show you. We can do this a little bit faster and do the whole thing. There we go. I want to make a clean copy of this and bring it down here so we can follow the process a little bit better. The idea of subtracting, two rational expressions, two fractions, is to make them first make sure they both have the same denominator. So what we can do is convert them. Well, I want to do one other thing before we do that. I want to write these denominators in factored form. That's going to help support converting them. All right, here's where we show. I'm backing up just like one little concept. The first fraction, right above where we're writing right now, 4x plus 2. I want to write this denominator, its original denominator in factored form, which is this. So watch, we're converting this, not converting, we're just rewriting in factored form, x minus 3 times x plus 4. This is going to help us in the next step. This is an intermediate step. And then we're going to start converting to the denominators of the LCD. Okay, next thing, next rational expression. We have 3x plus 8, but we want to write its denominator in factored form. Here's factored form for this second denominator. We have an x plus 2 times x plus 4. And then here's the minus sign between them. I'm just rewriting it. The only thing we did was we showed the denominators in factored form. Okay, I'm even going to slide this over just a little bit, the minus sign. And you'll see why in a second. Okay, now let's show what both of these denominators, what do we want them to look like ultimately? We want these guys to have a denominator of the LCD. So the LCD is x minus 3, x plus 4, x plus 2. We're going to convert this whole fraction, rational expression, to a rational expression that's got the blue LCD, this guy, as its denominator. And we're going to do the same thing to the second rational expression. So we're going to convert the second rational expression so that it also has the exact same LCD as its new denominator. Okay, how do we do the converting? We always do it with multiplying. Look, this guy, the first rational expression, has x minus 3. Of the LCD, it already has that factor of the LCD in it, in this first denominator. It already has the x plus 4 factor in its own denominator. But which one's missing, right? It's the x plus 2 is missing. This is a factor that's missing from this original denominator. So what are we going to do? Same way as it's times in with these other factors in the LCD, we're going to times it in to the rational expression. So what's missing, you identify what any missing factors in the denominator, and that's the only one that was missing. And then we copy up, always copy up into the numerator. And then it's going to be like, what's x plus 2 over x plus 2? This is a big 1. Anything divided by itself is 1. So we're allowed to do it. We're allowed to multiply the original rational expression by the red rational expression, okay? I have to make sure, though, with multi-term numerators, we mentioned this on Thursday last week, whenever I've got a multi-term numerator, I have to capture in parentheses before doing any multiplying. Okay, let's see what the second rational expression denominator needs. Because it only has 2 factors, but the LCD's got 3. See the blue LCD? It's got 3. So what factor is missing from the green denominator, the green second denominator? So let's identify. X plus 2 is already in this denominator. Look, x plus 2. That factor is already in the second denominator. X plus 4 is already in the second denominator. Then this is the one that's missing. This is a missing factor. Meaning the original denominator is missing an x minus 3 from if I converted it to be the LCD. It needs the x minus 3 to become the LCD, least common denominator. But that's all I'm missing, so we copy up x minus 3. Here's a giant 1 again. You know, so I'm allowed to times any rational expression or fraction by 1. It's going to change the look of it, but it's not going to change this rational expression's value, what it represents. I need to capture the numerator, multi-term numerator, 3x plus 8 in parentheses. Okay, next. I'm going to get rid of these so we have room to work. When I multiply straight across, let's make it green. When I multiply these straight across, like, you know, ready to multiply two fractions, I join with the common fraction bar. I'll do the same thing over here. Everything, numerators and denominators get times with their counterparts, right? And I see that up in this numerator, we have to do FOIL. These are two binomials. So when let's make clean copies so they're easier to look at. I'm just going to do 4x plus 2 times this red x plus 2. I'm just doing an intermediate area of calculation, and we're going to start multiplying. So I'm going to use FOIL. F in FOIL is 4x squared. The O in FOIL is positive 8x. The I in FOIL is positive 2x. And the L in FOIL is positive 4, is the L in FOIL. O and I are like terms. They're going to add up to positive 10. Let me do this as in black. Okay. Well, let's leave it like this. This will be easier to look at. See where it came from. Positive 8x plus 2x is 10x. There's nothing else combinable with 4x squared. And in other words, there's no like terms like it. And there's no like terms like a constant like positive 4. Okay, we're going to do the similar thing to, and let me show it like this. This numerator, we're just multiplying right here. I just broke out the calculation. Same way, I'm going to break out this calculation. Do an intermediate calculation right here. So we have 3x plus 8 times this x minus 3. And we'll start, foiling again. We're just foiling the numerator, binomials, right? So f in FOIL is 3x squared. O in FOIL is negative 9x. I in FOIL is positive 8x. And the L in FOIL is negative 24. These two guys are like terms, and they're going to make a negative 1x, right? If I'm doing that correctly. There's no like terms with an x squared, and there's no like terms with a constant. Here's this minus sign that's between the two fractions, right? Rational expressions. Okay, what are we looking at now? I'm just going to check these real quickly. Sure, I did the FOIL right. 4x squared plus 8x plus 2x plus 4. Yeah. Second FOIL is 3x squared minus 9x plus 8x minus 24. Okay, awesome. Once we're at this point, tell me, aren't the denominators the same now? I keep asking that until I say, yeah, they're both exactly the same. Yes, they are. They both are copies of the LCD. That means we can move all of this into one common fraction. Addition and subtraction, they never happen in the denominator. So we grab one of the denominators and copy it into the common fractions denominator. Okay, common denominator. It's plus 2. And move the green numerators, these guys, they're each going to get copied up into the common numerator. So first one is 4x squared plus 10x plus 4. The second numerator is 3x squared minus 1x. I'm just writing the 1 in for now. because we might use it for calculation. Make sure I copy this correctly. And then here's the minus sign that moves up from between the fractions up into between the numerators. Okay. Here's the place where many students is very common. They accidentally, inadvertently mess up the problem. If I continue from here, what I'm subtracting is only 3x squared. We have to do one more thing before we really do subtraction here, because if I only do minus 3x squared, I'm going to arrive at the incorrect answer. Okay, so look at what really is happening when you subtract a second fraction. It's got a whole bunch of terms in it, like 3x squared and 1x and 24. What really has to happen is I cannot leave off parentheses around the second numerator. And when subtraction moves up from in between the fractions to the numerator, the common numerator, now with the parentheses, it's going to change the signs of all three terms in the second numerator. That's critical. Okay, look at what happens. So I'm going to go ahead and copy this for a second. For me to remove these parentheses, those, I would say this. What is the opposite of positive 3x? See, this is like a positive 3x, and I would go negative 3x. I mean, opposite of positive 3x squared, I would say negative 3x squared. This is like the subtraction sign now works like negation. This negates, turns everything inside the parentheses to their opposites. Okay, what is the opposite of negative 1x? And you would say positive 1x. This guy, negative 1x, turns to positive 1x. And last one, it's like distributing negative 1 times, really, but it's even easier than that. I say, what is the opposite of negative 24? And you would say positive 24. Every one of those green terms in the black parentheses had to turn to their opposites, and now it's going to lead to the correct answer. I had to show you one like this because it's, when you only have a single term, you don't have to worry about it. When you have two or more terms, you have to turn every one of them to their opposites. Only in the second polynomial, we didn't touch the first one, left the first one alone. The 4x squared plus 10x plus 4 remains original, the way it came in from the first rational expression's numerator. Okay, let's, I'm just going to copy again to pick up a little bit of speed since we're in the digital domain here. And I'm just going to erase the numerator and we'll bring in the results, okay? Okay, what do I say when we go 4x squared minus 3x squared? That's going to be, I still have 1, you know what I mean? Positive 1, x squared. How about now 10x to the first and plus 1x? That's going to be plus 11x. And then what about this? I have 4, I have 24 more. Like these are the constants that are like each other. So what do we have? I have 28. I would almost be done, except for one thing. I have to make sure, this goes back to section 6.1, when we have a rational expression, we really need to think about simplifying it. So from here down, we've successfully combined the two rational expressions. I just need to think about factor the numerator. The bottom, the denominator is already factored, but are there any common factors in that trinomial that could have a common factor with the denominator? Any common factors between the numerator and denominator? So we have to factor and see. Okay, so I'm just going to do this one last time. This just helps me when I copy it from having to rewrite the entire denominator. You're going to come up with tricks too when you're doing your homework on paper, because these obviously they take a long time. All right, so here's, I mean, there's a lot of writing involved. Not a perfect squared trinomial because of the 28. Leading coefficient of 1. You know, we're factoring, right? Factor the green numerator. X times x. Factors of 28, whose sum is 11. So I'm thinking 4 and 7. There's not a lot of things that multiply to make 28. 4 and 7 are from the multiplication table. They're both positive. If I multiply the 4 and 7 together, we get 28. And when we add 4 and 7, we get 11. So these are good. I was just using the two tables method, right? Okay, what do we see? We see x plus 4. Does it find itself down here in the denominator? It does. The whole x plus 4, the blue one, is surrounded by nothing but multiply. It's fair game to divide out. And we go ahead and divide it out. Look, we did find a common factor, but we wouldn't have been able to recognize it without factoring, you know, this green numerator. And then I look again, like, is there any x plus 7s anywhere down here? No, those are different. So now I think we're done. Let's look over here. I'm sorry, these are like long, but they're good, you know. Look, so because they teach us a little bit of endurance, you know. 1 plus x plus 7 is x plus 7, and the only factors that did not divide out were x minus 3 and x plus 2. And this would be the correct answer in factored form, which is the popular form for you know, the section that we're in. This is like the most common way to show your response. Okay, and again, you know, don't divide out this x with anything. That x is an addend. It's not a factor. Last time x was involved in times was with plus 7, x plus 7, locked up with all those objects, parentheses 2 times 1. So you can't take this blue x up here and divide it into either one of these x's down there. Those also are locked up with first one with minus 3 and parentheses, and the second one with plus 2 and parentheses. So that x has nothing as a common factor sense involved with anything common in the denominator. Okay, that's our final answer for that one. Okay, my friends, let me, I'm going to switch now over to let's create a new whiteboard. And let's maybe make the background just different for fun. We'll have a little fun out of life. You know? And let's look for our textbook. So look, student practices, they're not worked out. So if you want to see an alternative set of steps, I think they're published in your book in a special section of the book that's included with what you purchased for our class. Okay, I want to go now to section 6.4. Let's get this guy started today, and we're going to finish this on Thursday's class. So section 6.4 now talks about rational equations. You know, now we're going to discuss equations, which we haven't done a little bit, you know, for a little while, because we're always kind of we've been focused on polynomials and factoring, and then now, you know, we've been doing the arithmetic of add, subtract, multiply, divide, simplify, and domain of a rational function. But now it's like back to solving an equation. An equation that contains rational expressions is called a rational equation. So they're talking about here is, you know, what we do is we find the LCD of all the denominators from every fraction across all the equation, left side and right side, and we multiply both sides, or you can say multiply every term by the LCD that we calculate, and it'll clear all the equation of fractions. So here's one example of that, and I want to make sure I'm following our plan. Yeah, let's do examples 1 and 3. So here's the first one. And maybe I can shrink this down. It doesn't matter. I'll just move this over and get out of the way in a second. Okay, just hang it over here, and we can maybe max this out and have this be visible. So this is section 6.4. I'm going to bring this back in just a second. Okay. All right. So we're all doing 6.2. Here's section 6.4. This is, the third section of module 5. So here's example 1. I'm going to slide this over just a hair. Example 1 shows us 9 over 4. Yeah, I'm just going to do that until I get it copied. Look, I'm just going to move this over to my second monitor and copy it over for you. It's in the recording if you want to pause it. Minus 1 over 2x equals 4 over x. I'm just making sure that I copied it correctly. 9 over 4 minus 1 over 2x equals 4 over x. And the instruction is solve. And then you could check your solution as well. Okay. All right. So the operative, thing that gets us going is solve. Solve the equation. Okay, because we haven't done these since before the midterm, like as far as discussing it in class, I just wanted to remind us in this discussion, when someone says solve an equation, what's our goal? Our goal for solving an equation is x equals a number, right? So similar to, and always, of course, positive 1. So here's our goal. Similar to when we did domain of a rational function, what am I worried about with when variables appear in the denominator of a fraction, which now we're calling rational expressions? Here's what I'm worried about. Are there any potential solutions? This is a potential solution. It has a potential for being the solution until I check it. And then only then, after I check it and it turns out true, does it become the actual solution. But right now, I'm talking about a potential solution. Are there any potential solutions, numbers out there, that when I put them into any one of these denominators, it'll cause the denominators to become a 0? Well, nothing's going to ever turn a 4 into a 0. No value of x is ever going to turn a 4 into a 0. But is there a value of x that could cause 2x to become 0 or x to become 0? So what the book and my math lab, they don't talk about this, but I would feel remiss to not share it with you. Similar way as we found the domain of a rational function. I like to share, before we create the LCD and multiply every term of the equation by the LCD, I'm saying, why don't we first calculate the domain of the entire equation. This is called domain of equation, the domain of the equation. This is a new first step. I only do this when there are fractions with variables in the denominator. That's that combination. 4 doesn't have a variable in it. I'm only worried about those potential solutions, any numbers that we can get at the end that would, if we put them in place of a variable, substitute in for the variable, they would cause the denominator to become a 0. And we can't have that. Division by 0 creates an undefined situation in math. A solution wouldn't do that. A proper solution to an equation would just cause a true to happen, not create a violation of math like division by 0, which is undefined. So that's what we're looking for as a new first step. Tonight, this in our discussion now, and on Thursday, we'll always find the domain of the equation first. To find any numbers, and we're going to label those as forbidden numbers from ever being allowed to be called a solution in the end. Okay, here's how we find the domain. Just like we did to find the domain of a function, we set every denominator that's got a variable in it, which is this 2x, that's got an x in it, denominator, and this x. This x. Hold up. I had to clear that out. One second. And this x right here. These are the two denominators. What are we worried about them becoming? 0. So we set it equal to 0. These are artificially created equations, just like we did for the function, domain of a function, rational function. And we want to solve for x. Solve both of these for x. You know what that's going to help us find is problem numbers for x equals a number. Are there any numbers that would cause denominators to be 0? Solving this. Any numbers for x that would cause the denominator to be 0? This would do that. This would help us find it. I got to solve this one by dividing by 2. And we get x equals 0. So, 0 divided by 2, that's 0. 0 is a problem number for this denominator, 2x. If I put 0 in for x right there, 2 times 0 is 0. 1 over 0, undefined. This is a problem number. I can never let a solution, a potential solution, I can never let this guy ever become 0. And look, the other equation, just by setting it equal to 0, it's already solved. This guy. So what's our domain? Our domain of the equation. I'm abbreviating the equation for a little bit of speed. In the end of this problem, x equals a number, right? This number, the potential solution, can be any real number as long as there's the pipe symbol such that, and I'm just making it thicker, it's too thick, such that x can be any real number as long as you never let x equal 0. If we got, in the end, we did all of our work and we got x equals 0, like find the LCD and all this is what we're about to do, you get x equals 0. And I'm like, wait a minute, 0 is not allowed. It causes that 2x and the x, those two denominators to become zeros. You know what I would conclude? No solution. That's the only number we generated. I would say there's no solution. Okay, that's where this is like very valuable. Okay, now let's go in earnest to the next step. And I'm just going to copy this real quick just to be able to see it because I got to zoom out. Let's move it down here. Copy it down here. And then we'll clean it up. Okay, so this is a 2x. And this is an x. Now it's time to eliminate fractions. And I'm saying fractions, just as a fast way to, instead of writing rational expressions, but these are really rational expressions. There's only one fraction is this one. The other two are, rational expressions. To eliminate fractions from the entire equation, we do two things. First, find the LCD. Second, we're going to multiply every single term by the LCD. Okay. So there's the end of the first step. Now we're eliminating fractions. First step in eliminating in finding an LCD is we list all the denominators, only the denominators. 4, 2x, and an x. I can't leave the 4 out this time. When you're finding an LCD, every denominator's got to be included in the calculation. Don't miss that point. Not just the ones that contain variables, all of them. Okay. All right. Next thing, let's factor everything with exponents showing. Factor. How do you find an LCD? List. Factor. Unique factors. Raise those to the greatest exponents that you find them. Okay. So list, here's all the list of our denominators. Factor 2 times 2, and I'm going to shrink it back down to proper prime factorization, prime numbers with exponents showing. This guy, we have a 2 to the first and x to the first. Really, all we did was add the powers to the first. This guy is x to the first. The 2x and the x were basically already factored. I just made exponents show. Now we're ready to populate, the LCD with one of everything different. unique factors. The LCD contains, right? Equals. And the contains is like another word that could translate to equal sign. One of everything different, one of every different factor in all the denominators. Well, 2 is the first of its kind. 2's need to be represented in the LCD. I hop over to the next LCD over here, excuse me, the next factor denominator over here. 2's are already represented, so I don't put another one in. But x's are different. X's are different from 2's, so x's need to be represented. These are going to end up getting multiplied together. The least common denominator is also the least common multiple of the denominators. Multiple, they're going to multiply. All these different factors in here. Okay, hop over to the last denominator. X's are already represented. We don't put another one in. Okay, and then here's the all-important final step of finding an LCD is greatest exponents. Greatest exponents on every one of those factors. So look, on 2's occur in this denominator and in this denominator. I examine their exponents. One's a 2 and one's a 1. The other one is a 1. So we have a 2 and a 1. Which one's greater? Greatest is the 2. I need 2's to be raised to the second power. On x's appear in 2 denominators, but they're both to the first power. Doesn't matter which one I grab it from. When they're a match, I need to put that match number on that factor in the LCD. Okay, that's it. The LCD is, I go ahead and expand using the fundamental property of exponents on the 2 to the second power and multiply. And we get the LCD is 4. For terms that are not fractions, I can use 4x with what's coming. Multiply each term by the LCD. On terms that are fractions, rational expressions, I need to use the LCD as a fraction by putting it over 1. They both mean 4x. But I use them appropriately for depending on the term that we're going to multiply. All right, I'm going to make a copy again of these. You can tell every time you use these original equations, I mean, you really could be writing and rewriting and rewriting until you're done. I have to do it to make sure that you all get the picture, a clear picture of what's going on. Okay, so please forgive me with a lot of rewriting. And I'm sure you're going to find your own shortcuts. Okay, I'm just making a little bit of room for what's coming, right? So if the first step was find the LCD for eliminating fractions, then the second big step is multiply each term by the LCD. This is the second big step of eliminating fractions from any equation. As you multiply each term, look, this 9 over 4 is a fraction. I need the LCD this way as a fraction. Second big term, it's like the first term. Second term is a rational expression, like a fraction. I need the fraction version again of the LCD, 4x over 1. On the right side, 4 over x. It's a fraction. It's like a rational expression, literally. I need the fraction version of the LCD. So in all of them, we needed this version of the LCD. Every term was a fraction. So complete the multiplication, right? Multiply straight across. I'm just joining these. Just like the next step of multiply. Look, if we calculated the LCD correctly, then every denominator is going to find itself in the LCD. That 4 finds all of itself. And this is the way we show division of common factors within a fraction. So the 4 took out the 4 in the LCD, but it leaves behind an x, and this 9 didn't go away. Those are going to wind up in the next step. Sometimes I factor elements, factors of the LCD. 4 can be expressed as 2 times 2, so I slash out the 4. I show it as 2 times 2, so that when I See this 2, it takes out one of the 2's in the 4 and itself, but it leaves behind a 2. There's an artifact of the original 4 in 4x, the LCD. This x takes out the entire x from the LCD. And so the only thing left up there is a 2 times a whole bunch of 1s. Look at what's happening with these denominators. 1 times 1, 1 times 1 times 1. They're becoming 1s, and over 1 is going to go away. It's exciting, you know, to a nerd like me. All right, so here's this x takes out that x, means anything divides into itself and leaves 1s behind. And here's another, the third denominator became 1 times 1 is 1. So let's summarize what we have. This is the big like resulting benefit. X times 9 up here, like I'm right here. X times 9 is better written 9x over 1 times 1 is 1. And what's that? Anything over 1 is better known as, you know, itself. Minus, here's this minus sign that's kind of creeping in from like it's been all crammed together. What do we have left? We got a 2 up there times all these 1s. I mean, that's times 1 is 2 times 1s are 2. 2 over 1 becomes, you know, 9x over 1, 9x. 2 over 1, 2. See how these are all becoming non-fractions, you know? All right, looks up what's up here. 4 times 4 is all that's left. Times 1 is like invisible, right? The identity for multiplication. 4 times 4 is 16, and times 1 is still 16. I don't see the 1s anymore. Like, you know, they become invisible to me in multiply. Over 1 times 1 is 1. 16 over 1 is 16. Guys, it takes a whole mess of words to describe this, but really, once you start cranking on finding the LCD and timesing it, and you don't have to explain it, it's going to go very quickly for you. What did this whole equation reduce to? A linear equation in one variable. Look, 9x minus 2 equals 16. That's from even, you know, a more fundamental level of algebra than where we're at. How do I solve this for x? You know, now that we've eliminated the fractions, you know, rational expressions from this, solve for x, it's linear. I'm going to get all the numbers over on the other side from x on the right side. This becomes 0. So we have 9x plus 0 is 9x equals 16 plus 2 is 18. And then we're going to divide both sides by 9, you know, to turn the coefficient of x into a positive 1. That's always a requirement for solving for the variable in an equation. But then we have to remember to balance the other side. Starts on the variable side. The whole, what do I divide by? 18 or 9? I do need to divide by the 9 to turn the coefficient of x into a 1. We want to tell someone what 1x is worth. What's 1x worth? X equals 2. 18 divided by 9 is 2. Okay. What about that domain? The domain. Where is it? I want to copy this guy and bring it all the way down to the bottom. Copy. Bring it down to the bottom. And see what that actually kind of, what does it mean, right? I mean, we know what it means. It's like never let x equal what? 0. Never let x equal 0. Well, we didn't get 0. We got a number that's not 0. We got x equals 2. So we're looking good by the domain. 2 will never create division by 0 in this problem. So we're in good shape by the domain. Now, if I want to take time to check x equals 2, by all means do it. In fact, we'll scroll down. The textbook's going to do it for us to save a little bit of time. Look at the difference in a solution set for this equation is, look at the, I want to write this so you see the difference between a domain and a solution set. X can be any real number as long as you only let x equal 2. See 2 coming in here? A solution set is what x equals. A domain sometimes has restricted, like forbidden numbers that x can never equal. See the difference between domain and solution set. Solution set specifies what the actual x number is. What we're going to tell someone, here's the solution, especially after we check it. So let's bring the textbook back and let's watch them check x equals 2. So they drop in 2 everywhere you see x, and the whole thing simplified to a true statement, 2 equals 2. Good times. Okay, we got the right number. Okay, I want to hop up and do number 3 here. This is a really good example because it's got its own little twists and turns. I just need to move it off to the side for a moment. And let's start a new whiteboard, okay? And I don't know, what did we have last time? Blue, let's do maybe gray. Okay. All right, I'll copy this guy, and then we'll move the textbook out of the way again, and we'll work on this problem. But you know what? This one's going to go faster because you know the process now. You know, it's understanding the process that means it's the most valuable thing. They can change the polynomials. We might use different methods of factoring. And it's the thing again, we're trying to get sharper at our factoring skills faster. Commit the factoring methods into our mind so we're more confident. With confidence comes accuracy and speed. It all happens if you just keep practicing. So this material is making you do all this factoring as part of finding the solutions, or part of finding, when you combine these two rational expressions, what do you get, right? You combine rational expression. So, but in this section now, we're solving equations. So here they come back down and just say, here's the equation, now solve it. Solve. Let me make sure I copied it correctly. Y squared minus 10 over y squared minus y minus 20 equals 1 plus 7 over y minus 5. This y doesn't look very nice. Here's y. All right. So we'll bring the textbook back, maybe check our work with it in a little bit. Okay. Solve a rational equation. Our goal is y equals a number. This is our goal. This is how we know when we're done. Solving the equation. Positive 1, y equals a number. So what's the ish? Is there any number, potential solution that would cause these denominators, any denominator, it's got a variable in it, to become a 0? Those are the two denominators in this problem. And I go, I don't know. I mean, I can kind of guess at the smaller denominator, never let y equal 5. If some of them are easy to deduce, but I don't know about y squared minus y minus 20. So this is when we do, let's just turn it blue this time. First, find the domain of the equation. This is what really nails it. Find the domain of the equation. Whenever you have variables in the denominator of any fractions, when you have rational expressions with variables in the denominator, this is really when you should start solving a rational equation with find the domain. So how do we do it? We set each denominator equal to 0. That's the fast way of saying it. I set each denominator that contains a variable equal to 0 because I'm worried about values of y that would cause the entire denominator expressions to become 0, right? So solve these resulting equations. We set each denominator equal to 0, and now we're going to solve them. So when I solve the first equation, I realize we've got a trinomial. It's quadratic, solved by factoring. This is what we have as our technique for solving by factoring right now. So when I factor this guy, I'm seeing like this. I just did the two tables method in my head, factors of C whose sum is a -1, which is B. When I times these two guys together, I get, no way, I missed, see it by checking them, I'm getting the sign right. This one needs to be a +4. By timesing these two guys together, I get -20. And when I add them together, I still owe $1 to somebody. So that's the two tables method. When you have two factors times each other equals 0, one of these two factors must be 0. So here's where we, state the 0 factor property. Either y minus 5 is 0, or the one factor is 0, or the other factor is 0. That's the 0 factor property step in solve a quadratic equation. Now solve the resulting linear equations. I add 5, and we get y equals 5. So this first equation. We subtract 4 from the second equation, we get y equals -4. So we're getting two solutions to these artificially created equations. Two solutions just out of one denominator right now. There's two problem numbers for the one denominator. We kind of talked about that when we did domain of a function, rational function. Look, I don't really have to solve this one because it's a duplicate of one of these equations. If I did, wouldn't I add 5 and get y equals 5 again, which matches this solution over here? All right. Replicate, duplicate, solutions, they're already represented. That problem number is already represented. So that's what I mean. You don't really need to worry about that last denominator. So summarize what we're doing. What we're doing is domain of equation. You can summarize our findings and say the domain of this equation is, by the end, look, I'm trying to repeat it enough times to where it clicks at some point. This number, look, this number, when I'm in a classroom, I can just point with a meter stick, right? This number, you can let that number be any real number, as long as, this symbology has that meaning. The set of all real numbers y. Y can be any real number as long as you never let y equal -4 or 5. Both of these are problem numbers for this equation, in one denominator or the other. And some of them, the 5 is bad for both denominators. Now let's move on to solving the equation. So I'm going to just copy this real quickly. Copy. And paste it down here. And what we're about to do is we're going to find the LCD and multiply all three terms by the LCD. There's 3 terms in there. Okay, so now it's down to, we're going to come back and check any solutions we get against the domain. Now's the time to actually solve the entire equation. So we're going to do the same 2 steps. First, find the LCD. Calculate the LCD. Steps of finding the LCD are: step 1, list out all the denominators. List. What do we have? We have this guy is y squared minus y minus 20. We have this other guy, there's only really 2 denominators, and y minus 5. And then we factor them. Well, you can recycle some of what you've done, Like, didn't we have to do factoring to solve this domain issue? It's y minus 5 times y plus 4. You can reuse that. Y minus 5, y minus 5 times y plus 4. Show exponents this time, though, just in case. And that's a times dot between them. You don't even have to show the times dot. This guy factors as these 2 factors. How do you show y minus 5 in factored form? We talked about that a little bit last Thursday. Because you just wrap parentheses around something that doesn't have a GCF. There's only one of itself. So I do show the exponent of 1 to the right of the closing parenthesis. Now we're ready to assemble the LCD. The LCD contains one of every different kind of factor in all the factored denominators. So what do we have? The LCD contains, well, first thing we run into is a y minus 5, first of its kind. Y plus 4 is different. It's different from y minus 5. We have y plus 4. Hop over to the other denominator, and I see y minus 5 again. Those are already represented, so we don't put another one in. So one of everything different. And then the all important greatest exponents. But here's a shortcut. All we ever saw were ones. I never saw any exponent bigger than 1 in this problem. You can automatically throw 1 on everything. But if I held to the process on y minus 5, I see y minus 5 in both denominators, factor in both denominators, but they're both raised to the first power. It doesn't matter which one I grab it from. Y plus 4 only appears in this one denominator, only to the first power. I just never ever saw an exponent rise to being greater than 1. So you can throw 1s on everything. I'm sure you are probably thinking about that too. Okay, how can we use the LCD? Let's clean it up one more level. Y minus 5 to the first power is y minus 5. To the first power goes away. It's still there, but doesn't need to be written in. Y plus 4 to the first power, these first powers can go away when you're summarizing the results, okay? But I also need to be prepared to use the LCD in fraction form, rational expression form, by putting it over 1. I'm going to use it one way or the other. They both have the same value. Over 1 is okay. I'm going to grab this this equation and copy it. Copy it right there. Let's copy it, paste it down here, at least so it's visible. I might spread things out a little bit. What happens if I do that? It just makes it bigger. I need to spread it out. Here's another thing that we did before in the last equation that we solved. We rewrote this guy. With denominators in factored form. Denominators in factored form. The y squared minus y minus 20 factored as y minus 5 times y plus 4. You want to show your denominators in factored form. The y minus 5 in factored form looks like y minus 5 with parentheses around it. Good to go. Okay. One last thing. When we are trying to eliminate fractions, the step 2 is, sorry, that's a bad step 2. Yeah. Step 2 is we're going to multiply each term by the LCD. So here it comes. Ready? Times this term by the LCD. This first big term right here is a rational expression. It looks like a fraction. So I'm going to use the thing that the LCD is a fraction appearance, the way that it appears as a fraction. So here it comes. Y minus 5 times y plus 4 over 1. What does that get us? It gets us to the line up numerators and denominators. Okay. So let's come back to that. Here's the same LCD, but this time I'm timesing a 1 by the LCD. This 1 is not a fraction. So now I need the LCD is not a fraction version. So we go times this 1 by this version of the LCD, which is y minus 5 times y plus 4. Then we got to times this whole term by the LCD. If this guy is a fraction, it's a rational expression, so I times it by the fraction form of the LCD. This form of an LCD. Look, I have to say one other thing. When we're when we were just adding two rational expressions together or subtracting two rational expressions and combining them, right, with add or subtract, you're only timesing by the missing factors. Do you see what I'm doing here, though? We did this already in the first example in 6.4. What I'm doing here is I'm using the entire LCD 3 times. It's especially apparent on this one. You know how this guy, y minus 5, is already got that part of the LCD? So if I was doing something like converting it to have the denominator of the LCD, the way we do when we add and subtract fractions only, I'd only be timesing it by y plus 4, and that happens in the denominator. This looks similar, but it's different. I'm multiplying by the entire LCD, not just the factor that's missing, the y plus 4. Don't confuse this operation with converting fractions so that you can add them together or subtract them together. Okay? When you're using the LCD for equation solving of rational equations, you use the entire LCD every time, for every term. For every term, you're using the entire LCD. Okay? It's a big thing that students do by accident. You don't mean to because you just haven't done a lot of these. I'm just trying to help prevent some frustration. All right? Now we're going to multiply straight across. Multiply these two guys straight across. But what should I do with y squared minus 10? I should capture in parentheses. Any multi-term numerator or denominator, when you do multiply, should put parentheses around them. But single-term numerators like this 7 over here, there's no need to put that 7 in denominator in parentheses. It's just a standalone factor. Okay, I hope that helps. Now we're going to divide out common factors. Look, this y minus 5 finds itself. This, mostly I'm doing the other way. The green y minus 5 in the denominator finds itself in the LCD. When you calculate the LCD correctly, it's going to contain every factor of every denominator in your equation. Every factor in the denominator finds itself in the LCD if you calculated the LCD correctly. Y plus 4 divides into itself. Why do you want the denominator factors to find themselves in the LCD? So that this happens, you know, that every factor in the denominator becomes a 1. They're all going to times together, make a giant over 1, and in the next step, it's the fraction is gone. I mean, look, in the numerator, 1 times 1, 1 times 1 times y squared minus 10 is y squared minus 10. Beautiful. This is what we want. That's why we're doing this, is to make the fractions go away. Because what's in the very next step if I stay on this term? Y squared minus 10 over 1 goes away. You're done. There's the end of fractions on the whole left side of this equation. Okay, now let's move to the right side. We're going to have to FOIL these. These have to, 1 times these are, we're going to have to FOIL that. Let's come back for a second. I want you to see, let's come back in a second. I want you to see this. In this guy, I want you to see the fractions go away. This denominator, y minus 5, finds itself in that blue LCD. Anything divides into itself and leaves 1s behind. Beautiful. All right, so what's left up there? We got a 7 times the blue y plus 4. That's a artifact, remaining factor of the LCD over 1 times 1 is 1. Man, awesome. Over 1 goes away. I just wanted you to see the fractions go away, rational expressions go away. Now let's come back and multiply these two guys. We need FOIL to do it. So the F in FOIL, y times y, y squared. O in FOIL, y times positive 4, positive 4y. I in FOIL, negative 5y. L in FOIL, negative 20. You know what it's going to create? The original, fraction. The original trinomial that we had is, oh, not x. This is y. Plus 4y, but I owe somebody 5y, that's minus 1y. Negative 20, and y squared. There's no terms like any of those. These are all unlike terms. So now when I copy these down here, we're good to go. What should I do next? Look, all the fractions are gone. Probably simplify. Like I'm looking at parentheses, right? So distribute the negative or the positive 7 times y is positive 7y. Positive 7 times positive 4, positive 28. Yeah, I might carry these guys down. This is all these terms are from multiplying, foiling the two binomials. Here's just, I'm trying to keep everything on the whole equation together, left side and right side. Okay, combine like terms. We still got more stuff over here that are combinable. We have negative 1y plus 7y. What's that? This is like 6y. We got minus 28 plus 28. It's like 28 minus 20 is 8. And then we've got y squared. Those are all unlike terms. So we're done simplifying the right side. What's the one on the left side? We've just been carrying down this y squared minus 10 since we eliminated the fraction. This is an equivalent fraction, presuming that we did all our arithmetic correctly, calculations and everything. It's equivalent to the very first. I mean, look. This equation is equivalent to the original problem if we manipulated the equation correctly. But it's way more simplified and there are no fractions. But what did this guy end up becoming by the time we're at this point? It's a quadratic equation. We got y squared. So where do I go from this point? There's no autopilot. It's like this is a quadratic equation. So I solve it using factoring. That's the method that we have in our course at this point. So I'm going to drag everything over to one side, meaning use add and subtract to make one side equal 0. We need standard form to solve a quadratic equation by factoring. I'm going to do it by, there's just less terms. If I, subtract y squared from left side and add 10 to the left side, we're going to get 0 plus 0. And that's going to be 0 on the left side. This is going to create standard form for a quadratic equation. So what do? I got to balance the equation by subtracting y squared and adding 10 to the right side. We're balancing the equation, right? We're doing the same things we did to the left side to make 0. And look, I mean, I didn't intend this to happen. It's just happening. That's y squared minus y squared, 0. This equation is no longer quadratic. I carry down the plus 6y. 8 plus 10 is like 18. It's not like 18, it's 18. 0 plus 6y, that's 6y, plus 18. When we rewrite what we thought we were headed to standard form for a quadratic equation turned into a linear equation, y to the first power, linear equation. How do I solve linear equations? Switch gears again. This went from a rational equation to a quadratic equation, and now it's a linear equation. You got to keep rolling with the changes. For linear equations, we eliminate the constant from the variable side and make it reappear when we do the additive property, addition property of equality. And over here on the left side, we get negative 18 equals 6y plus 0. 6y plus 0 is 6y equals negative 18. Finish solving for y. Divide by 6. So that the coefficient of y becomes a positive 1 times y. Got to remember to balance the equation. This is the multiplicative property of equality, multiplication property of equality, goes by several names, by dividing also by 6. Negative divided by positive makes negative. 18 divided by 6 is 3. 1 times y is y. Flip the two sides around. Negative 3 equals y, then that means if I flip the sides around, y also equals negative 3. Two things are equal one way. as they are the other way. Okay. Y equals -3. Time to check our domain. Are -3s even allowed? Or do -3s cause denominators to become 0 in the original equation? I don't know. Let's grab the domain, copy it, take it down to the bottom where we are. Domain says, because I can't remember what was in the domain. You know, why should I? It's written down up there, right? All right. We got y equals -3. Are -3s okay by the domain? Yeah. Domain says only -4 and -5 are the problem numbers. This gives me confidence in -3 not causing undefined division by 0. And it didn't take a heck of a lot of time to find the domain by setting those denominators equal to 0 and solving. It's worth it. Otherwise, I've got to check every single potential solution in the original equation if I don't do the domain. More on that in Thursday's class. Okay, I got one lined up that's going to help us see the light on that. So here's the solution set. I just want to make it clear that one more time. Y can be any real number in the end, as long as y only equals -3. Here's how you show a solution set. And how it differs from a domain right here. Domains, not all domains have restrictions, but this one does. We got 2 problem numbers. Never let y equal -4 or 5. But if the book checks, look, let's have this. Let's look at a quick peek, and see if they agree. Does y equal -3? It sure does. So look, here's their check step. See how when you put -3 in place of x everywhere, left and right sides of the equation, we get 1/8 equals 1/8. That's what a solution is supposed to do, not cause undefined like division by 0. See, -3 actually, everything turned out great. It's beautiful. So we can answer the problem with confidence, -3. So we and the book agree. My friends, I hope you get a lot out of this discussion that we had tonight. I look forward to seeing you in Thursday's class. And remember, I'm going to send you a link for this recording as soon as it's finished processing. All right. So I look forward to seeing you. If you have any questions on this, we'll talk about it in Thursday's class. Be well, my friends.